Today's discussion: factors affecting the rate of enzyme catalyzed reaction. The rate of a reaction catalyzed by enzymes is influenced by several reaction conditions or factors like number one, temperature, number two, enzyme concentration, number three, substrate concentration, and number four, pH. Now we will discuss one by one. First, temperature, how it influences the enzyme function. You see the curve I have shown here. In the x-axis, I have shown the temperature, and in the y-axis, I have shown the enzyme activity. Now, each enzyme has an optimal temperature which is in narrow range at which its activity is maximum. At temperatures significantly lower or higher than the optimal temperature, there is drastic loss of activity. Thus, when the reaction temperature increases from lower to higher, there is gradual increase in activity till the optimum temperature is achieved, at which the rate of reaction is maximum. The increase in activity occurs because the number of molecules entering into the transition state and overcoming the energy barrier increases with rise in temperature, which imparts the kinetic energy to the molecules. Hence, there is sharp rise in activity with the increasing temperature. Further increase in temperature ultimately leads to denaturation of the enzyme with precipitous loss of activity. In human body, reaction occurs at 37 degrees centigrade, which is the optimum temperature. Certain bacteria living in hot springs will have enzymes with optimum temperature near 100 degrees centigrade. This property is exploited in certain molecular biology techniques like polymerase chain reaction or PCR that you will learn later on. Second one factor is enzyme concentration. Under standard conditions, the rate of reaction is directly proportional to the enzyme concentration if adequate substrate is added. That I have shown you in the picture. Again, in the x-axis, it is the enzyme concentration, and y-axis, it is the enzyme activity. And rate of reaction is directly proportional with the enzyme concentration. If enzyme concentration is double, the rate of reaction is also becomes double. And the maximum activity is achieved when the whole enzyme is saturated with the substrate. The third one, substrate concentration. The activity or rate of reaction increases with increasing substrate concentration, that's shown as S in x-axis, and the rate of reaction in y-axis. However, the enzyme activity or rate of reaction is not directly proportional with the substrate concentration. The curve plotted between substrate concentration and the rate of reaction or enzyme activity is the typical hyperbolic curve with a plateau indicating nearly the maximum activity. In the picture you can see the initially at relatively low substrate concentration, the activity increases almost linearly, but with further increase in substrate concentration, smaller and smaller rise in enzyme activity occurs. Finally, a point is reached beyond which further increase in substrate concentration leads to an almost invisible or an infinitely small rise in activity. At this point, enzyme activity is nearly equal to maximum activity. This reflects almost a saturation point where all the enzyme is saturated with substrate. In such a situation, there is no obvious problem of measuring the maximum rate of reaction, which is ever changing by a very small rate of change. Finding out the exact maximum rate of reaction is almost impossible. Hence, the exact relationship between substrate concentration and velocity cannot be defined by this curve. The maximum velocity obtained is called Vmax. It represents the maximum reaction rate attainable in presence of excess substrate at substrate saturation level. Km value is substrate concentration expressed in moles per liter at half maximal velocity. It denotes that 50% of enzyme molecules are bound with substrate molecules at that particular substrate concentration. Km is independent of enzyme concentration. In the curve, Km is indicated at half Vmax. If enzyme concentration is double, the Vmax will be double, but the half Vmax Km will remain exactly same. Other words, irrespective of enzyme concentration, 50% molecules are bound to substrate at that particular substrate concentration. Influence of pH over enzyme catalyzed reaction. Like temperature, enzyme activity is maximum at its optimum pH. At pH much lower and higher than the optimum pH, the enzyme activity is very low. The enzyme, being a protein, acts as an ampholyte having both the positively and negatively charged groups participating in catalysis. pH, which is an indicator of hydrogen ion concentration, alters the dissociation and change on these groups. This alters the enzyme activity. Hence, the enzyme activity is low on either side of optimal pH. Most enzymes are optimally active at neutral pH in our body. Some exceptions are pepsin pH range is 1 to 2. Acid phosphatase pH range is 4 to 5 and alkaline phosphatase pH range is 9 to 10, at which pH range all these enzymes act best. Now let us discuss the enzyme kinetics. The study of rate of reaction of an enzyme catalyzed reaction and the various factors affecting it is referred to as enzyme kinetics. This is change in response to changes in experimental parameters. Now, enzymes enhance the rate of reaction enormously, 10 to the power 7 to 10 to the power 14 fold, as compared to an ordinary uncatalyzed chemical reaction without enzymes. How this happens? Kinetic theory of reactions and thermodynamic considerations help in understanding this role of enzyme. Now, the energy barrier. If the energy contained G0 of the reactants is recorded as they undergo a chemical reaction, the change into products, it is seen that the change in free energy occurs during the course of reaction. During the reaction, reactant undergoes a state of highest free energy before converting into product. This state is called transition state. The free energy level of transition state is much higher than that of either the reactant or the product. This difference between the free energy of the transition state and of the reactants is called activation energy. The magnitude of activation energy is the energy barrier between the reactant and the products. In the transition state, the reactants are in the state of highest free energy during a chemical reaction. It is highly unstable state in which the reactants have a very high probability of transformation into product or even converting back into the original state of reactants depending on the equilibrium constant and net free energy change that I have shown you in the picture. In the middle part of the picture, you will see E plus S, that is enzyme plus substrate. K1 is the rate constant which helps in forward direction to form enzyme substrate complex, and ultimately K2, another rate constant which forms enzyme plus product. Now the ES complex may revert back by rate constant, that is K minus 1, again to enzyme plus substrate. So it is not a stable reaction intermediate, but a very brief point in the course of reaction when the reaction is at the top of an energy hill. In the transition state, a large number of molecules have sufficient energy to overcome the activation energy barrier and undergo collision to increase the rate of reaction significantly. Now, what enzymes do? Enzymes act by lowering the activation energy. They decrease the activation energy barrier so that more molecules can undergo transition state and form product. Enzyme lower this energy barrier by forming the enzyme substrate complex as an intermediate in the reaction. This intermediate formation is reversible and occurs by weak non-covalent interaction. It is essential for formation of product. E plus S equal to ES equal to E plus P. Formation of each weak interaction between enzyme and substrate is accompanied by small release of free energy. Large number of such interactions lead to the release of significant free energy. This total energy derived from enzyme substrate complex formation is called binding energy. This binding energy is used by the enzymes to lower the activation energy. The formation of ES is optimized in the transition state. Here I have shown you the substrate concentration in the x-axis and again the reaction velocity in the y-axis, where there lies the first order reaction where the reaction is a rapid one, but as the concentration of substrate is gradually increased, all the enzymes become saturated and maximum velocity is gradually attained, where zero order reaction takes place. Now, the significance of the different depiction: S stands for substrate, E enzyme, ES enzyme plus substrate complex, P product, and I have already told you that K1, K minus 1 and K2 all are rate constants. Next comes Michaelis-Menten equation. It describes how reaction velocity varies with substrate concentration. Michaelis and Menten explained the relationship between substrate and velocity by a mathematical equation called Michaelis-Menten equation, which is V0 equal to Vmax S by Km plus S, where V0 initial rate of reaction, Vmax maximum rate of reaction, Km Michaelis-Menten constant, S substrate concentration. S substrate concentration. The Michaelis-Menten constant of Km is defined as the concentration of substrate at which the rate of reaction is equal to the half of the maximum rate of reactions. Since it is substrate concentration, its unit are moles per liter, and Km Michaelis constant is equal to within bracket K minus 1 plus K2 bracket close divided by K1. And S here I have depicted is the substrate concentration. This Michaelis-Menten equation is very important from your examination point of view. This you must learn nicely.